Hey everyone, welcome to designing a URL shortener. Let's dive into the system design.
Welcome back to Code Architect. Today we're designing a URL shortener like bit.ly. This is a classic interview question, testing your ability to handle scale. Our goal: to take a long URL and create a much shorter, unique alias. When a user visits the short URL, they're redirected to the original. We need a system that's highly available, handles millions of requests, and ensures unique short URLs. Let's dive in. Let's clarify requirements. Functionally, we need to shorten URLs, redirect short URLs to their original targets, and optionally support custom short URLs. Non-functionally, the system should be highly available, fault-tolerant, and handle a massive read-to-write ratio. We'll prioritize availability over strong consistency, leaning towards eventual consistency. This is an important CAP theorem consideration. We aim for low latency for redirects and reasonable latency for URL shortening. Let's estimate scale. Imagine 100 million new URLs shortened per month. That's roughly 40 QPS for writes. Assuming a 100.1 read-to-write ratio, we're looking at 4,000 QPS for reads. For storage, if each short URL entry takes 100 bytes, we'll need about 10 GB of storage per month, totaling around 120 GB per year. Projecting 5 years of growth, we'll need around 600 GB. These are rough estimates to guide our design decisions. Here's the high-level architecture. Clients send shortening requests to an API gateway, which routes them to our web servers. A load balancer distributes traffic across these servers. The web servers interact with a database to store URL mappings and a cache for frequently accessed short URLs. For redirection, the process is similar, but the cache and CDN play a crucial role in minimizing latency. This layered approach allows us to scale individual components as needed. Let's choose a database. While no NoSQL options like Cassandra offer scalability, we need strong consistency, especially for custom URLs, to ensure uniqueness. Therefore, we'll use a relational database like MySQL. A junior engineer might be tempted to use NoSQL for everything, but we rejected it here because it compromises our consistency guarantees. Our data model will have at least two columns: short, URL, primary key, and original, URL. We'll need indexes on both columns for efficient lookups. Now the core, URL shortening. We'll use a Snowflake ID generator to create unique 64-bit IDs. Then we convert these IDs to base 62 encoded strings using characters AZ, AZ09. This gives us short URLs. A junior engineer might consider UUIDs, but they're large and not sequential, which hurts database indexing and cache locality. Snowflake ensures uniqueness in sequential IDs. Collision resolution isn't a concern with Snowflake's guaranteed uniqueness. Let's scale the read path. Caching is key. We'll use a CDN to cache frequently accessed short URLs at the edge, minimizing latency for global users. Additionally, we'll implement a caching layer, like Redis or Memcached, in front of the database. Load balancing distributes read traffic across multiple read replicas of the database. GeoDNS can route users to the closest CDN or data center, further reducing latency. This multi-layered approach ensures fast redirects. Scaling the write path requires sharding. We'll shard the database based on the Snowflake ID. Consistent hashing ensures even data distribution across shards. When a new URL is shortened, the Snowflake ID determines which shard it's written to. This allows us to horizontally scale the database by adding more shards. Leader election ensures high availability for each shard. This avoids bottlenecks on a single master database. For analytics and click tracking, we need to capture click events. We can use Kafka to ingest these events in real time. These events are then processed and stored in a data warehouse, like Hadoop or Snowflake, for analysis. MapReduce jobs can perform aggregations and generate reports on click-through rates, geographic distribution, and other metrics. This provides valuable insights into URL usage. Security is paramount. We'll implement rate limiting to prevent abuse and DOS attacks. API authentication ensures that only authorized users can create short URLs. We can use techniques like token-based authentication, JWT for this. Regular security audits and penetration testing are essential to identify and address vulnerabilities. This protects the system from malicious actors. Effective cache invalidation is crucial. We'll use a TTL, time-to-live-based invalidation strategy for the cache. When a URL is updated or deleted, which is rare, we can proactively invalidate the cache entry. For heavily accessed URLs, we can use an LRU, least recently used eviction policy to ensure that the most frequently used URLs remain in the cache. Supporting custom short URLs adds complexity. We need to ensure uniqueness of custom URLs. Before creating a custom URL, we must check if it already exists in the database. We can use a unique index on the short URL column to enforce this constraint. We also need to handle cases where users try to create very long or invalid custom URLs. So we've designed a scalable URL shortener, prioritizing availability and handling a massive read-to-write ratio. The core trade-off was latency versus consistency. Potential improvements include exploring more sophisticated sharding strategies to minimize cross-shard queries for analytics. Diving deeply into optimal sharding strategy and its impact on minimizing cross-shard queries for analytics, with a focus on consistent hashing and its variations, e.g. jump consistent hash, and how they can improve cache hit ratios across shards. Thanks for watching.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.